Let's start with the first project, Housing Price Predictor. In this, we are given a data set with lots of house features such as their area, number of bedrooms, number of bathrooms, and we have to predict the house price if a new piece of information comes in. We are going to do a lot of things in this project, and most of the things, one way or another, would be followed in every other single ML and AI projects. So let's go ahead and see what are we are going to cover as part of this project. First step is problem definition. That means we are trying to understand who we are building this for. Like, is the direct consumer, like someone from their laptop is going to use it, or we are passing it to some another software or another API and they are going to consume it. Then we also need to understand what are their requirements, what are they looking for exactly, how they will use it. Something like this to make our ML model better. I'll explain later how this is useful. Second is data collection. Most of the time we are already going to use data which is openly present. It can be on Kaggle, it can be on Scikit or somewhere else. Then is data processing. Data pre-processing involves that clearing out the data, clearing out null values. If we need to perform some transformation on the data, some feature engineering, something like that. Then we have model selection. What kind of model we will need to use, whether it's linear regression or whether it's random forest, neural networks or whatnot. Then we have model training. In model training, we will evaluate on different parameters, how to get a good accuracy, bad accuracy, how to fix the params and all. Then evaluation and then deployment. But as you can see, there are many areas which are repetitive. For example, if you see this, sometimes when you're deploying, you feel that, okay, I'm not getting the good accuracy. Then you start this whole process again. So this is a never ending process because ML needs to keep on learning. As you might already know that no ML model is 100% accurate all the time, unless it's a very simple data. So we need to keep on training it to make it more and more and more better. We'll explore each of these steps in much more detail. So let's move ahead. The first part is problem definition. So what does it mean? So let's say that rather than just predicting the house price, what you're doing is you're passing this data to another software. And what the software wants to know is whether the houses lies in class A, class B, and class C. And let's say that class A is something like greater than 100K. B is 80K to 100K. C, D, E, something like this. Then this changes our problem, right? Previously, what we were doing, we were directly finding the house prices, whether it was 120K, 119K, and so on and so forth. But now it has gone to class A, B, C, D, E. Based on what we want, what our requirement is, our ML model completely changes. That's why it's important to understand that what we want to achieve, who our user is, and what they actually want. So now in our case, we want actual house prices that our ML model should predict that give any given new data set, number of bedrooms, number of bathrooms, and other data, our model should be able to predict new prices. That is our requirement. So we have made this clear. Second thing is understanding the kind of training supervision our model needs. For example, in cases where you have a data, okay, and for all of this data, you have output given as well. This kind of model is known as supervised training model. Why? Because some supervision has been provided to the model. For a given few examples, we know what our output is. So that means we have provided some supervision, right? So this is known as supervised training model. Second one is unsupervised training model. As the name is already clear, in unsupervised training model, we only have the data, but we don't have output. This is not present. This is known as unsupervised training model. Sorry. Yeah, this is known as unsupervised training model. Now, even in supervised, we have multiple cases. So if you look at supervised training, I showed you two examples above. What was happening in the example one, we were predicting the house prices. That means 100K, 120K, 110K. These are all housing prices which we were going to predict. In the second example, we were supposed to evaluate classes, whether the housing price lies in class A, class B, class C, or class D, something so forth. Now, when you have this variable data where the values could be, from one range to another range, this normally lies in regression. But if you want to predict your data into some particular classes, this is known as classification. Another example for classification could be that suppose you have digits, images of digits, 1, 2, something like 9 in different formats. It could be paper cuts, it could be some drawing or something else. And you want to classify which number is it. So basically an image processing model which will classify that image belongs to which number. So now what will happen? Based on these images, you want to output whether the number is 1 or 2 or 3 or 4. These are images, okay? And these are numbers. Now this is again category of classification. Why classification? Because output is of limited size, right? It can be either 1 or 2 or 3 or 4 or till 9. So this is another classification problem where you are classifying your entire data in some particular categories. So now based on our above housing prices, you already know that it's supervised, right? Why? Because for each of our data, we are also given estimated price. That means for our training data, not only we have given input, but we are also given prices. So that's why it lies in supervised category. Now another thing is, since prices are numerical numbers, which can range from like 100K to 2000K or something like that, it lies in regression problem. Why? Because it's a variable data. There is no constant categories for which we need to find the data for, right? So that's why I asked that it's important to understand who our user is and what they want. So if you evaluate for class A, B, C, Ds, it will lie in classification and your ML model will be according to that. Versus if you predict the housing prices, it will lie in regression model and your ML model will be according to that. So now we know that, okay, it's regression and supervised. There are also other training models other than supervised and unsupervised, such as reinforcement, which we will cover later. So for now, let's go with this. Okay. Now, before moving further, let's talk about the most commonly used notations in ML. This is very common and used everywhere. M. It represents as the number of training data sets you have. If you have to consider in the tabular form, then you can say number of rows. Number of rows or number of training data set. That means if you have housing prices, let's say you have 4 features, some bedroom size, some location and bathroom, something else. And let's say you have 5 rows, 1, 2, 3, 4, 5. Then M is 5 in this case. Okay. Second is known as X. The bigger and bold X represents your entire input data set. This is input training set. Then you have small x with I. What this represent? This represent your ith row. For example, this one is represented by x2. Okay. Then we have xi and then j. What this represent? Jth feature of ith row. That means x2 represent the second row, but let's say you want this feature, this particular feature, then it will be x22. If it is this one, then it's x23 because it's third feature. 1, 2, 3, 4. Okay. So J represents a column basically, and I represents a row, if you want to understand in simple terms. And then we have similarly, we have a Y that represents output. And if you annotate it with YI, then it represents the ith output. So basically for each corresponding row, you would have a price, right? You would have a price for each corresponding row. So this is represented by Y5 because this is the output of the fifth row. And then we have Y cap. This is the predicted output. Basically what your model predicted. Your model will not predict the actual values, right? It will have some kind of hallucination, some kind of error, something would be there, right? So if you pass some kind of input row, let's say you pass that I have 2 bedrooms, 3 bathrooms, and let's say I have like area 500 square feet and something feature. And what you predicted is, let's say 20K, and the actual price was 80K. Then this actual price is represented by Y, and your predicted, this is predicted, which your model predicted. This will be represented by Y cap. You don't have to memorize all this. As we do it more and more, we use it more and more, it will automatically get fit into your head. So don't worry. Now, lastly, we have a cost function. What cost function represents? It represents how much your model is off by actual values. That means whenever you create a model on a training set, you will also train that, you will also find whether it's right or not on test set, right? So in by using the test set, you will find the cost, that how much difference is it from actual values. So there are many ways to calculate cost function. There are many openly used cost function available, but one of the most common used and also which we will use is MSE, mean squared error function. It is represented by 1 by 2m sigma I is equals to 1 to m, and then we have predicted values minus our original values square. Basically what we are doing is whatever we are predicting versus what the actual value is, we are finding the difference between them for each row, and we are doing the summation of it. The intuition behind it and why is it useful, I'll upload it in another video because it will involve some math. But currently, as you can see, if the difference, let's calculate it for a value. Let's say m is equals to 1. Okay, to keep it simple. And let's say that y predicted is 5 and actual value of y is 2. Then what will be the MSE? MSE will be 1 by 2. Since it's summation over one value, so it's directly 5 minus 2 square. This is 3 square 9 by 2, that is 4.5. Right? Now let's say suppose our predictor value is 4. And our actual value is still 2. Let's make it more closer. Let's say our predicted value is 3. And our actual value is 2. Now what would be the MSE? It would be 1 by 2. Then we have 3 minus 2 square, which is nothing but half, which is 0.5. So you can see that the closer your predicted value to actual value, the less cost function is, or the lesser the MSE is. So basically our job is to minimize the cost function. The lower the cost function, the more accurate it is. I hope this is clear. Cool. So next class, we'll start with the code. We'll learn how we can fetch the data. We'll learn how we can perform operations on it. We'll learn how we can play on it and all those things.